Hello, everyone, and welcome to our course that Edwin Brady from St. Andrews is so kind to present. He's the creator of the Idris programming language, and he's done lots of other interesting things like the white space language that many of you may have seen.
Well, not seen, actually. That's.
You just need the right editor. So he'll be teaching us about Idris and dependently typed functional programming. So thanks for coming.
Okay, thank you, David. Thank you, first of all, to David and to Hannes and to Peter for organising this and getting me over to Copenhagen again. It's great to be here. And good to see so many of you here interested in learning about dependently typed functional programming. So I should say before I start, I'm trying a little bit of an experiment here in screen recording. You might have seen me fiddling with QuickTime just there. So if this works, there'll be a recording of this afterwards, and you'll be on the internet. So say hello to the internet, everyone. Hello, internet. Hello. If it doesn't work, then, well, never mind. Anything could happen. What I'm going to talk about for the next 4 lectures is the Idris programming language. This is the language I've been working on initially as a kind of part-time hobby project, but I gradually found it becoming more and more the thing that I did all of my real work in. And I decided it's about time that I started sharing this language with the world and getting other people to see what they can do with it. So there's going to be lectures and exercise sessions. Roughly an hour of lecture, although they might overrun a little bit, and then an hour of exercise sessions. So if you want to take part in the exercise sessions, naturally you'll need to have Idris installed on your laptop. I've just released a new version onto Hackage. So if you type all of this stuff, Cabal update, Cabal install Idris, then you should, fingers crossed, find that things work if Cabal works and if you have all the relevant libraries installed. There's a couple of problems that I know there's a few laptops open. So have people managed to install it? Yeah, thumbs up. If there's any problems with that, just come and find me during the exercise sessions. We'll sort it out. There's a couple of common problems, but they're easily fixed. So I'll say a little bit about what the lectures are going to be all about, just to give you a feel for what you're going to learn. Firstly, they are necessarily going to go at a fairly fast pace. So I'm kind of assuming that you all have a background in functional programming to some extent. So do people know Haskell? Anyone not know Haskell? Do you know Haskell to read if you don't know Haskell? So if you know Haskell to read, that's fine. If you know what a type class is, yeah, everyone knows what a type class is. So I guess that means you've pretty much all got the background that this should be okay. But it will necessarily go at a fast pace. I wouldn't necessarily expect you to know everything, to do everything automatically by the end of the course, but I'll give you a flavour of what it's all about, and you can obviously carry on in your own time. So today, I'm going to do a fairly rapid tour of the language. I'm going to show you how the system works. I'm going to show you a few features, a few programming idioms. And I like to do things by live hacking at my laptop, which means that at any point, this doesn't go for the people who are listening to this on the internet, assuming this works. They can't shout, what happens if. But your privilege of being in the room is you can shout, what happens if, while I'm typing code. And I'll maybe try it. If I know it's going to go wrong, I'll probably make an excuse. But if it's something that might work, we'll give it a try, see how things go. So obviously you'll want to see examples of why you should learn another programming language, what's interesting about Idris. So the second and third lectures are going to be about basically the kind of things I like to do with dependent types. I'll show you a few new language features as we go. And then eventually, if we get to it, if we don't overrun too much, I'll tell you a little bit about some of the interesting things I've learned while implementing Idris, so some basic techniques that you need to implement a dependently typed language that actually works. So, what we'll have to... This always happens, doesn't it? Just as you're getting into your stride, the Mac... I'm actually just teasing. The thing about software, isn't it? Is software never quite does what you want it to do, and it always fails at really inconvenient moments. I've done that gag too many times now, and I'm not. It's almost like it's expected now. Yeah. Software always fails when you least expect it to. I mean, there's never a convenient time for software to crash, is there? And what this is all about, to me, in the end, is coming up with new ways of making it possible to write software that actually works as early as you possibly can. With less time taken in testing and in verification, less time taken in getting software that actually does the right thing. So this sort of thing, home machine crashes, well, okay, they don't happen that often, but they're kind of annoying when they do. This sort of thing happens quite a lot more. This is my revenge on Preview, because when I got this new Mac, it had obviously the new version of all the Mac software. And the new version of Preview had this great feature whereby it crashed every 5 or 6 times I updated my slides. So I don't use Preview anymore. But this, you're all kind of used to this sort of thing. It happens all the time. This sort of thing, you may be less used to this sort of software. Does anyone recognize this? You know what it is? Because you were at my summer school, so you've seen me use this picture before. Okay. This is an artist's impression of the Mars Climate Orbiter, which was sent up to Mars in about 1998, I think. This is an artist's impression of the Mars Climate Orbiter because NASA were having trouble finding photographers to go with it. The other reason it has to be an artist's impression is that instead of orbiting Mars when it got there, it crashed straight into it. And it turned out the reason it crashed straight into Mars was a bit of a mess up with dimensions. One, in ground-based software, some people were working in metric units, some people were working in imperial units. So basically, it was a type error in the ground-based software that caused several $100 million worth of hardware to crash into a planet. Now, what you or I do if software doesn't work, if it crashes, we just fix the bug, recompile it, and run it again. If your development cycle is 6 months, because that's how long it takes to send a new thing over to Mars, that's really less of a useful way of developing software. So ideally, you want some way of knowing before you run your programs that they're going to work. I'm not saying we've solved this problem, but I'm saying that if you have if you have a sort of type-based methodology, you might get somewhere further. Okay, so. Idris is a programming language with dependent types, so with a very strong type system that you can say more about what your program is going to do before you run it. I describe it as a general purpose programming language, which it's kind of I'm not even sure what that term means anymore, to be honest. I used to call it a practical programming language, but then I thought, well, it's not for me to say what a practical programming language is. That's for the users to say. Then I called it a systems programming language, and people got offended because it had a garbage collector, and they say you can't have a systems programming language if you have a garbage collector. So I've eventually resorted to general purpose, and that basically means you can compile things and run them. Now, this isn't necessarily this shouldn't be novel, but somehow in world of dependent types it is kind of novel, because you get people saying things like, well, I proved my program correct, why would I run it? I know it's going to work. I want to run my programs. I want things to happen after I compile them. So the reason I asked earlier if people were comfortable with Haskell is just because the syntax of Idris is heavily influenced by Haskell. There's pattern matching, there's where clauses, do notation, just the usual high-level stuff that you might expect from monad comprehensions. There's only a couple of minor differences in syntax. One is that I use a single colon for the typing judgment rather than a double colon. Sometimes there's a small cheer from a corner of the room when I say that. So this is the sort of thing that people get very agitated by. So yeah, single colon instead of double colons, and there's a few minor things just to cope with language features that we'll see later. And this is the key thing. It has what I call full dependent types. So that is, there's no syntactic distinction between types and values. So you have a typing judgment, value colon type, and the value and type, they have the same syntactic form. Obviously, they have different semantic forms, but types can appear wherever you like. Types can appear in terms can appear in types, and well, we'll see as we go through the week what this actually means for how you build your programs. The important thing that this means really is that you can encode properties of your programs, you can check properties of your programs, so you can know what properties your program satisfies before you run them, so that you can know, for example, if you can encode main colon doesn't crash into Mars, then you know, because the type checker said so, that your program isn't going to crash into Mars. So other things that support that, so tactic-based theorem proving. Anyone have any experience with Coq? Quite a few, actually. That's a bit more than I thought. So, Coq has a very, you could call it a dependently typed programming language. You could call it a theorem prover. There's a bit of a, there's not exactly a clear distinction between these two things. But if you're proving theorems in Coq, you'll typically give it as a script containing tactics. So Idris has a similar kind of thing, but it's not the primary way of building programs. And the main thing I'm interested in is implementing domain-specific languages. So allowing domain experts to implement and reason about programs in their own problem domains. So Idris has support for implementing embedded domain-specific languages and some particular kinds of notation to deal with that, which we'll see as we go through the week. Right. So I guess we should see a little bit of code. That would be nice. Let's see what programs actually look like. And the traditional way to start is with natural numbers, lists with length. The kind of data declaration we have here, this is just like you would see in Haskell. So this would equally be valid Haskell. So natural numbers are either 0 or the successor of another natural number. Not a particularly good way of implementing numbers in a computer because we have it's going to take, I don't know, how much memory is it going to take to store maxint? Most of it, I think. We'll see later on that this isn't actually a problem, but for now, let's just accept that we have unary natural numbers. We can define polymorphic data types. So a slight change in notation here. If you're familiar with GADTs in Haskell, then this is something you'll have seen before. But so just another way of declaring data types, where rather than giving the Haskell style algebraic data type declaration, we give explicit type constructors for the type and all of the constructors of the data type. So list, it takes a type as a parameter and returns a type. So it's just a function from types to types, and type is the type of types. I used to call the type of type set following Agda and Coq, and obviously we had a very long discussion on Twitter and mailing lists about whether this should be set or type, because this kind of thing is a kind of discussion that everybody can contribute to, so everybody does. Eventually, I went with type, because type is the type of types, and that's a type. So it's called type. I think that's a fairly reasonable conclusion to come to. So type is the type of types. There's a bit more to it than that, but we'll get into that. We'll not get into that quite now. We may get into that a bit later on. So once we've got that, we can say that explicitly nil has type list of sum A. So we're implicitly quantifying over A, so A is just some type. And then cons, this is an infix operator. So just like Haskell, you can declare and define infix constructors. We don't have the restriction on names that Haskell does, so they don't have to begin with a colon if they're constructors. But you can define arbitrary infix operators. And this takes some A and some list of A and gives us back a new list of A. So all very straightforward so far, yes? Just an ordinary polymorphic data type. You should, by the way, feel free just to intervene and ask questions at any time. You've all been very polite so far. There's no need to be polite. You're very welcome to heckle. Within reason. I heard a chuckle there that sort of just sounded like someone's up to something. But no. So polymorphic lists, just like Haskell, OCaml, anything. Things get more interesting when you start making more precise, more explicit type declarations. So vectors, this is a slightly unfortunate name, but it's a name we're stuck with. The dependent types community has always called lists with length vectors. So I guess we better carry on calling them vectors. So a vector is just a list that is parameterized over its length. Now this is the reason we had unary natural numbers, because they have a structure, 0 and successor, that corresponds nicely to the structure of lists. So nil has length 0, cons has length successor of its tail. So a vector, the nil vector has length 0, and to make a non-empty vector, we take an element, a vector of length k, and that gives us a vector of length successor of k. So notice, by the way, that I've used the same constructor name for lists and vectors. This is in general allowed by Idris, provided that the names are declared in different modules. So we've got a module system that's essentially just namespaces. And these will be disambiguated by their type. So wherever you've got a nil or a cons, the type checker will look at what the type is, and it will decide accordingly. I would recommend not doing this too much, because obviously you can end up in a lot of trouble if you have a million things called nil. But in general, you can overload just in an ad hoc way. So once you've got data types which have some parameter that specifies some invariant of that type, so vector, we've got a parameter nat that expresses the invariant, the length of that list. Then any functions you write over that data type will also tell you something about those invariant properties. So if you're appending one vector to another, you've got a vector of m things, and you've got a vector of n things, it's quite natural that the append function will tell you what the relationship between m and n is. So the relationship between m and n is, well, it's just m plus n. So m is a natural number, n is a natural number. We have type classes. We can overload plus just like as if it's an ordinary number. So this is what's going on here. Plus is a function over natural numbers that add them together. So if I try to give something a definition here that doesn't respect the property that the output is the length is the sum of the input lengths, I'll get a type error. I'll show you that a bit later on. I won't show it on this slide. But this type here tells you what the invariant properties of that function must be for that function to be accepted. Question, yes?
Just try to type in reverse append, which reverses x, just to see what happened. Is that an easy one, or is it a difficult one in Idris?
The difficulty will be you have to prove the property that m plus n respects what you've done. Now, the reason this works without any proof is because of the way plus is defined. So I kind of glossed over that for the moment, but I'll just try to explain it briefly. So the length here is 0, and the length here is n. And plus is defined by analyzing its first argument. So there is a definition 0 plus n equals n, which means that the expected type here is going to be n. Similarly, successor of n plus n is defined as successor of the whole thing, which means, again, this type is going to work just without any further checking. If you reverse things, there's going to be a little bit more work you have to do. It's not too much work, but you do have to do a little bit of theorem proving. And a little bit later in this lecture, I'll show you how that works. And then maybe we could look at it even closer more closely afterwards if you want to. Right, so another function, another sort of thing that you might see regularly is working with two vectors or two data types that you've explicitly said to have the same invariant. So here we've got two vectors as inputs. We've explicitly said that they have the same element type, and we've explicitly said they have the same length, and we've explicitly said that the output has the same length as the inputs. So this is a function that takes two vectors and adds the corresponding elements in each vector. So empty vector plus empty vector gives you empty vector, and x cons x's plus y cons y's gives you x plus y cons add the rest. So the most interesting thing about this is that by looking at the type, you can tell that there is no point in writing clauses for an empty vector and a non-empty vector, because that won't type check, because the two lengths are then different. So the compiler can look at this and say, well, that function is defined for all inputs. That will always terminate, because you can look at this vadd and you can see that the x's and y's are smaller than the input, so it's always going to get smaller. And you can see that all the cases are covered, because any other cases are simply not going to type check. And we can basically tell the compiler that that's a property we expect of that function. So we can add this keyword total. Basically says to the compiler, please check that this function is terminating and covers all inputs, and report an error if it isn't. So in that sense, you can. So the way it checks this is just by looking at the structure of the function. So it's not a particularly clever check. We haven't magically solved the halting problem here. It is conservative. It's not going to find every possible total function, but it means that you can have that added confidence that your function is defined for all inputs. This becomes particularly important if your function happens to be a proof, say. So if you're trying to prove something, you really want to know that that function that you've written hasn't cheated in any way by not defining a case or by doing some circular reasoning somewhere.
But is it still sort of fairly straightforward to define non-terminating or non-total functions?
Yeah, you just don't put total. Yeah, that's all you have to do. So this is, remember I said there was this sort of, what's the distinction between a programming language and a theorem prover? Well, I don't actually know what that difference is. I've never come up with a definable answer. It's just, to me, this feels like a programming language because you can do that sort of thing. You can write non-total things if you want to. It doesn't feel like a theorem prover because, although it does have a theorem prover underneath, because you're not forced to be, total functions are the exception rather than the rule. Now, this upsets some people, but then every design choice you're going to make is going to upset somebody. So there you go. There you have it. So yes, you can just do it. So before I get into live hacking demo, I want to say a little bit about why we even care about dependent types. So before I go any further, I guess I should check that is everyone comfortable with what I mean when I'm talking about dependent types? Is there anyone who would like me to explain that just a little bit more? You're generally happy with that? Okay. So I maybe mention at this point that the asking questions technique that I picked up from Philip Wadler. He said if you're not sure whether other people, whether you're the only person in the room who doesn't know the answer to something or doesn't know something, nudge the person next to you and say, do you understand what a dependent type is? And if they say no, you then know that there is at least one other person in the room who wants to ask the question that you're about to ask. So, just don't feel shy about asking questions. And if you do feel shy, just nudge the person next to you until you say no. Right, why dependent types? Well, it's all about being more precise about what you mean for your programs to do. So here's a program called sort. Takes a list of int as input, gives a list of int as an output. So I guess we can all come up with some suggestion for what this program is supposed to do. It's, yes?
Clearly it should return the empty list.
Correct. It should return the empty list. So there is nothing stopping it. So as far as we're all concerned, this is clearly meant to sort some things into either ascending or descending order. Or some kind of order. As far as the compiler is concerned, this function takes a list and returns a list. Great. So we can be a bit more precise. We can now rule out David's idea that this function is supposed to return the empty list. David, what's this function supposed to do?
It's the identity function, clearly.
Yes, indeed. So we've been a little bit more precise here. It's ruled out some wrong implementations. Yeah, reverse would be fine too. We've ruled out some wrong implementations. We haven't ruled out all wrong implementations. So we could be a bit more precise. So I've just invented some data types here. Permutation x's y's is just a predicate that says x's is some permutation of y's. This notation here, by the way, it's a dependent pair. It's this first element in the pair here is allowed to be used as part of the type of the second element here. So you can read this almost as an existence proof. There exists a y's such that y is a permutation of x's. So this will return a pair of the new list and the proof. And I'm going to ask David again. What do you think this function should do?
Clearly it reverses the list.
Reverses the list, clearly. Yeah.
Basically with a proof that shows that everything
Yeah.
is pretty good.
Now, you can see, even though we haven't fully specified sort, we're getting more and more precise. We're ruling out more and more wrong definitions. We're just making it harder to write these functions. So there's clearly some kind of trade-off here. We can make types as precise as we need for whatever our application happens to be. It might be that we simply don't care whether sort works. Actually, sort is the sort of example that people use for showing theorem provers, how to prove that the list you've got is sorted, your sort algorithm works. But I think we've pretty much nailed sort as a community. We've pretty much worked out how to do that. So I don't find it a particularly worthwhile example. But this does at least show you how, if you're going to do a full correctness proof, things can get quite tricky quite soon just in writing down the type. So there's a trade-off to strike between how precise you want the type, and how much you're willing to let slide.
Don't touch the green slime.
Sorry?
Don't touch the green slime.
Don't touch the green slime. Indeed. Right. So we're going to see in the rest of this course some examples of how to program with dependent types. We're going to see how you use more precise types for setting up machine check proofs of correctness. So proofs of properties of your programs that the machine says yes or no to. We are going to work under the slightly unconvincing assumption that the Idris type checker is perfect, because if we don't do that, then all software has bugs in it. Let's just deal with it. As a general rule, by the way, Idris, any bugs in the Idris type checker I find these days tend to be it rejecting programs that should work. I haven't found it accepting a program that shouldn't work and be reloaded for quite some time. So that is slightly reassuring. But we have to work under that assumption because, it's software. That's a whole different philosophical question of how to trust a machine check proof. I'm going to talk about two different kinds of correctness. So functional correctness, which is basically, does sort, return a sorted list, and extra functional correctness, which is basically things like, are the resources we have available correctly managed? So, do we run out of memory, or did we remember to open the file before we read it? That kind of thing. These actually clearly argue those are quite closely related. Also going to talk about not just correctness. So correctness is the usual selling point for dependent types, but we can also talk about generic programming, which is writing better libraries, giving better types to your library code. We have first-class types. So one way of describing a full dependently typed language is that, just like we say, functional programming means that functions become first-class citizens. Dependently typed programming means that types become first-class citizens. So we can do computation with types. We can generate new types. Type can be calculated by programs, so we can write more generic programs. As another side of that, make more expressive libraries. And this is the key selling point. I will never write a monad transformer again, and you'll find out why in lecture 3. Very quickly, I want to say why Idris rather than any of the other languages. I don't particularly want this to be me saying never use any of the other languages, because I don't think that at all. There's AGDA, another dependently typed language. There's Coq, as I've mentioned earlier. Epigram is in development. And these all bring different things to the field of dependently typed programming. I think we're at a stage in designing languages with dependent types where we don't actually know the right way to do things. So to be honest, I'd encourage you all to go and write your own dependently typed language after this, which corrects all the things that everyone else got wrong. And then, maybe in a few years' time, we'd all come together and work out what we should be doing. Basically, that's one reason I designed, I came up with Idris, is that I think there's plenty of scope for experimenting with different design features, different ways of doing things. And it's just easier to do that if you have your own system to work with. It's nice to have the freedom to be able to make some kind of language design decision, either with high-level notation or with termination checking, all of these things. Idris is still at a stage in development where anyone could contribute to that. So if you have suggestions you want to make, things you want to do, now is a good time to do it. And then, of course, in the end, as I said earlier, I want to actually write programs that run. So it's a desire to think about how types affect compilation. Can we get efficiency from very precise types? So having a compiled language to work with to do that is a good thing to do. Okay, so that's enough talk from me. I think it's time to do a bit of hacking and show you how things work. So if you have a laptop open, then you should be able to play along with this and try other things and see what goes wrong or what goes right. So it's by law I have to show you this program. So you'll notice that this is quite similar to a Haskell program. It just doesn't have a where here, and it has a single colon here. What I've done there So if you type Idris and then the name of your file, you'll end up in this read eval print loop, a bit like GHCI, similar commands to GHCI. So what I've done here, :C, compiles to an executable. So that's now, if I quit, I can now actually run this thing, and it says "Hello World." Some astonishment! I've actually run a program already. We're only one program in. I've already run it. Don't worry, I won't be running any more programs for a while. But we will try writing one, and maybe we should try writing this one together, since we've got a basic understanding of Haskell and an idea of what a dependent type is. Here's the first exercise. So we're going to write a function called vapp, and that's going to take a vector of functions and a vector of arguments, and it's going to return that each function applied to the argument. So where are we going to start? We'll start with vapp, I suppose. We should remember to type a single colon. I get caught out by this, by the way, when I'm implementing Haskell programs. I keep writing a double colon for lists and a single colon for types, and the error messages are just as confusing. Well, they're not quite as confusing as the ones Idris give when you do it the other way around, but they're still quite confusing. So a vector of functions, that'll be, well, the function type is just AROB, just like that, and it's going to have a length, and the arguments are going to be of type A, I expect, and there's going to be, well, how many of them are there going to be? It's going to have to be n, otherwise this isn't going to work. And what's that going to return? It's going to return a vector of b's with any luck. So we can type check that function declaration. The thing about having more precise types is that you have to think a bit more carefully about your function declarations, and it's quite useful to type check them before you even get going on your program. So that's good. The type declaration type checked. Good start.
What are the bounds of A and B here?
Good question.
Or
yes.
Where is it quantified?
So
what is implicit and what is explicit?
that's a good question. I was going to come to that a little bit later, but why don't I do it now? So when you're running a Haskell program, you often have type variables in the type declaration, and Haskell will look at them. It'll see their type variables, and it'll assume their types. You don't have quite so much freedom in a dependently typed language, because those variables could be any type. Now here, this A is a type, this B is a type, and this N is a natural number, because we know that. But Hannah's question is, how does Idris know that? Well, what it does is it looks for things, names in the type which are unbound, so free names in the type. So here we've got A, B, and N. It checks, well, if they begin with a lowercase letter, it makes the assumption that if they are unbound, they need to be quantified over. So they become implicit arguments to this function. So effectively, we've got a type that is a bit like this. These curly braces mean this is an implicit argument. So you don't need to give it when you call the function. And Idris will fill it in for you. Now, obviously, it's a bit boring to have to write all of that every time you write a function declaration. So you don't have to. It'll figure it out for you. Sometimes you do have to give the compiler a bit of a hint. Sometimes it's a little bit harder, particularly if one of your implicit arguments is a dependent type, sort of chaining dependencies. But for this definition, we'll only need the variables. Right. So, what's the answer going to be? Empty. You reckon it's empty? I think it's probably empty too. But let's just what should we call? Foo. That's, again, by law, I have to use foo within the first 40 minutes, or I lose my computer science license. So this question mark here means I don't know yet. Please tell me what the type is. Please give me some kind of clue. So if I type check that, it says yes, that's okay. But I haven't fully defined this program. It's clearly not going to work yet. If I type :m, it'll tell me which meta variables are still to fill in. So you can see. Can you see this low down on the screen? That's okay. So there's still basic2.foo to fill in, and I can ask what the type of that is. And yes, it's expecting it's going to provide a vector type B of length 0. So the only thing that's going to work there, obviously, is an empty vector.
Does it infer that n is a mat just from the lowercase n?
It infers n is a gnat from the type of vect. So the type of
something I missed.
the type of vect is type to gnat type. Yeah. Okay. So if I've got a vector, if I've got a function and some more functions and an argument and some more arguments, then, well, the first thing I'm going to do, because this drives me crazy, I'm going to apply f to the argument, and then I'm going to just recursively apply the remainder to the list of arguments. Okay. I guess we could try running that, couldn't we? Can we think of a function of one argument? How about I don't know if this is going to work now. How about that? If we apply +4 to, I don't know, 38, and then maybe +5 to 37. That's reassuring. Gave us the right answer. So unlike GHCI, there's not an implicit show call going before everything here. It's just going to give you the raw term. So I've used an operator section here, just applied +4 to 38, +5 to 37, and it's given the answer 42, 42. So yeah, we can run functions at the redevelop print loop just to try them out. Okay, so much for basic usage. That's kind of enough to get going and get the system running. Try a few definitions. Remember, you can always this meta variable notation, the query foo I was using. I find that incredibly useful with dependent types because it's often quite hard to work out exactly what the type is you need to fill in at a particular point, and it's quite useful basically to get the system to tell you. So I don't know. I think I know what goes here. Not entirely sure what the type is. Please tell me. So that's what the meta syntax, the meta variables are all about. So a couple of more introductory things I need to say. By default, we're using strict evaluation. So this is really just because, it's partly to be gratuitously different from Haskell, but it's really because I want to be able to reason about the performance to some extent of the programs. Can't really reason about performance, but you can at least have some kind of predictable performance of your programs without worrying too much about what gets evaluated when. However, sometimes you want to write things like this. So this function boolean, you can also read this as if then else, I suppose. This is actually how if then else is implemented internally. So we got take a boolean and then two arguments, and if the boolean's true, return the first one. If it's false, return the second one. Great. You do that in Haskell, that sort of thing, all the time, defining control structures, because you're taking advantage of laziness. The problem comes when you check the expression and then you evaluate this large expression and this large expression, and then once you've evaluated those two expressions, you look at which one you needed and then return it. Well, clearly that's not the way you want to write programs if you want to write anything remotely efficient. So Idris allows you to annotate things as being lazy. So this vertical bar before the function type, so you have to give an explicit name if you do that, but this vertical bar before the function, before the argument type means please evaluate this argument lazily. Only evaluate it if it's needed. And now, when you've got this if then else, I should use boolean rather than if then else, but never mind. When you've got this if then else, these expressions will only be evaluated if they're actually needed. So this means that even though you don't have laziness, you can implement your own control structures just by explicitly saying to the evaluator which arguments should be delayed until they're needed. Right. So I said a little bit about theorem proving, and theorem proving plays a big part in dependently typed programming simply because as soon as you have precise types, it's going to take eventually a little bit of work to get your programs past the type checker. So thanks to the Curry-Howard correspondence, we can view types as specifications and programs as proofs of specifications. So there's a little example here, some familiar example from logic. You could define OR, the OR connective, as being either a proof of the first thing or a proof of the second thing. So it's either A or it's B. And then you can define the connective AND as being a proof of both things. So then I can write little theorems like this. If I've got an A, so A implies A or B, and I can prove that by saying, yes, it's the first one. And if I've got an A and a B, I can prove A and B. So A implies B implies A and B. So you can read the function arrow as an implication. So yes, I can prove that by saying, well, I've got both of them, so here you go. So here we have some very simple proofs, the kind of thing that you see, in undergraduate computer science courses. We never tell undergraduates that they're writing programs when they do proofs. Maybe it would help if we did. Or maybe it would scare them off. I don't know. Never tried this experiment. But you'll see what's going on here. That it is basically just constructively showing by giving a constructor how the proof is built. Now, AND and OR aren't particularly exciting. We were actually basically pairing and the either data type in world of Haskell. Proving equalities is rather more exciting. So here is it's sort of a built-in type in that it's not part of any library. It's not an extension to the type theory or anything. It's just it's something that you get free when you start up Idris. This is the equality type. So we've got some input type A, some other input type B, and that gives us an equality type. Notice A and B are different, by the way. So, but the only way we can ever prove that two things are the same is by them actually being the same. So the only way of proving A equals B is this constructor REFL that says, okay, X equals X. So if you can somehow convince the machine that both sides of an equality are the same, you're then in a position where you can apply this constructor and you have an equality proof. We also have an empty type where I've attempted to ASCII-artify bottom there. This is a proof of false. So if you ever make one of these, then hopefully you've got a contradiction somewhere, because otherwise you're in trouble. So the only way you'll ever build one of these is by having two things that are unequal. So once you've got an equality, you can do rewriting in your types. So if I've got a proof that X equals Y, and I've got some property of X, then obviously I can have that same property for Y, because I have a proof that X equals Y. So here's an example of the kind of a simple kind of reflectivity proof. So the type here, 2 plus 2 equals 4. How do you prove that 2 plus 2 equals 4? Well, it just is. So the type checker will normalize this. It'll evaluate 2 plus 2 and it'll get 4. So basically that's how you convince the type checker that two things are equal. You persuade it to normalize. So 2 plus 2 equals 4. So we can just use REFL to prove that. Right, so you got to see how that works in practice, because obviously proving that 2 plus 2 equals 4 is not a particularly useful thing to do. Proving that X equals X is not particularly useful. So there's got to be some way of actually building more realistic versions of more realistic proofs. Okay. So I believe I put it in plus theorem. That would be a good place for it. Right. So I'm going to try to prove that n plus 0 equals n, which I think we all agree that it is. This is something that it should be possible to prove. Just for reference, actually, I should have put this in earlier, but I'll put it in now. Plus is defined like this. Again, I can't resist it. So what this will mean is if I ever see 0 plus y somewhere, if the type checker ever sees 0 plus y, it can replace it because it knows that 0 is in some canonical form, so it can reduce. Given that this is an n, it can't reduce. So the only way I'm ever going to persuade the type checker that this is okay is by somehow persuading this first argument to reduce. The way I'll persuade that first argument to reduce is by pattern matching. So if that's 0, then what are we going to return? Any guesses? 0 plus 1. 1 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 plus 1. REFL should work. Yep, happy with REFL. What about in this case? Any ideas what we're going to reduce? What we're going to put here? It's a bit harder, isn't it? Let's ask the machine for help. We don't have to work on our own here. We've got a machine that can help us. This is the great thing about static typing. Static typing is not a stick to beat you over the head with. Static typing is an assistant that tells you what you should do. So I don't know about you, but if I'm working with a record in Haskell and I'm adding a field, what I do is I add the field, hit compile, and see where I have to change. I don't go through my program checking myself because I've got a checker to do that for me. Anyway, let's just call it that. So I can now ask the machine what the type of that case is, and it'll give me a hint. So I've now got to prove, well, that's not entirely surprising. Successor of k plus 0 equals successor of k. But again, I don't really want to have to work that through myself to work out exactly what the construction is. So we can drop into proof mode. So :p gets us into an interactive theorem proving mode. And thanks to David, I could complete that. That was nice. Theorem proving mode gives us a list of premises, of which we have none so far, and then the goal, the thing we're trying to prove. So it's far easier if we reduce things to normal form in this case. So at this prompt, I can apply tactics, so for rewriting or for introducing things into the context, applying functions. One tactic I can apply is called compute, and that just reduces everything to normal form. So now that's telling us that successor of plus k0 equals successor of k. Now, we know that plus n0 equals 0 because that's what we're defining. We can define that, define that inductively. It gives us a hint what we have to do. Oops, I didn't need to quit there. Gives us a hint what we have to do is basically get ourselves an induction hypothesis from somewhere. So we can apply our theorem to k. So that's okay. It's structurally smaller, so it's still we've still made some progress. Do the same thing again. And we have a thing. We have a premise here that says plus k0 equals k. We've got a plus k0 here. So if we rewrite this by this rule, we have a left-hand side and a right-hand side that are equal. So let's do that. So this is applying that replace function that I showed you a couple of slides ago. So rewrite by IH, and yes, left-hand side and right-hand side are now the same. Woohoo! And we've won. Trivial. We say trivial, and it says I agree. Now you might wonder what happens next. So I've done this proof, and I'm just back at the prompt. But then I had a program, and you don't really want to be typing in these proofs every time you load your thing up into the environment. So there's a command called addProof, which just adds it to your source file. What this allows you to do is write a structure of your proof. So here we've got a structure that says, clearly this is a proof by induction, and then we're going to do some work. And then at the end, it's kind of like an appendix. So if you're reading an academic paper on a programming language, you'll often find that it's full of lemmas, and it'll say proof, see appendix, or see technical report. Well, this is the technical report that comes with your program. It's a list of proofs that come at the end. This gets more important when you're writing actual programs, because it means you can separate the theorem proving from the actual thing you mean the people to read. So, as Idris and Sussman said, programs are for humans to read and only incidentally for machines to execute. So this allows you to separate all the boring details of the proof from what your program's actually doing. Okay, we better get on with it because supposedly I've only got 10 minutes left of this lecture, and I'm not very far through it yet. Is it okay to overrun a few minutes? And I was kind of expecting to overrun into tomorrow's anyway. So, right now. I'm not going to go through all the different language constructs because most of them will be things that you're familiar with from Haskell or whatever your favorite functional language is. So, case constructs, pattern matching, if then else, all of that you have. Or you can at least implement yourself. Something that is slightly awkward, though, is case analysis of dependent types. So the thing about dependent types is that the type of one thing can tell you a bit about the form of another. So if you know that x is a vector of length 0, for example, then you know that the length is another argument. You know that length is 0, because you already know from the length of the vector. And vice versa. You know if you have a length of a vector 0, you know it's going to be a cons. You don't have to go any further. This is a bit awkward for the case construct, because case only matches one thing at a time. And it doesn't tell you anything about how it's affected the patterns on the left-hand side of your definition. So the with rule is just a means of introducing new patterns on the left-hand side, effectively. So I'll demonstrate that by implementing another function. This data type here called parity. It basically says that every natural number can be categorized as even or odd. So it's an even number. If it's an even number, you've got an index n plus n, and if it's an odd number, you've got an index successor of n plus n. Now, at this point, you all have to agree that this is a reasonable characterization of natural numbers, and even and odd can be expressed in this way. So the universal thing really about if you're proving the correctness of a program through types is you have to agree that the types really say what you mean. Because if you don't agree with that, well, you haven't proved anything. So if you agree that this is a reasonable definition of the parity of numbers, then if you can write this function, for all n in nat, there is a parity, so every number has a parity. If we can write that function and say it's total, then basically we've proved this property. Every number has a parity. Yeah, let's implement that. You'll, by the way, if you look on the wiki page at the end, there's a list of exercises and a link to some code. So all of this code is stuff that you have available, so you can you can see where we're heading or edit it as we go. So we've got the beginnings of a definition. Well, how are we going to do this? I guess we better do this by inspecting n, because that's all we've got. So what's the parity of 0? That'll be even, I suppose. And it's not quite clever enough to identify that that while unifying n plus n and 0, that both of the n's must be 0. So we have to tell it. So if you have so n here is an implicit argument to parity. You can say what you mean the implicit arguments to be just by giving this syntax: name equals value. So here I'm explicitly saying that the n must be 0 here. And then the parity of 1. Thank you. It would almost have been better if you hadn't pointed that out, because then you could have seen what the system does. But since you did, I don't have to show you. I think it just says no type declaration for pair tie, so it's, I think it's reasonably sane. Even? You didn't tell me that even was wrong, though, did you? Okay, happy with that so far. This next bit is where I'm going to get my crib sheet out, just because. Now, what about other numbers? Oh, for goodness sake! It's very kind of you to say you thought it was intentional. Now, what are we going to do here? Well, firstly, I'm going to get my crib sheet out, because if I'm going to get this wrong, then we'll be here all day. What do you mean we're not here all day already? So I can't just do case analysis on k, because, well, it's not going to tell us. Not really going to tell us enough. What I can do, I can't even check the parity of k. So if I check the parity of k, it doesn't really tell us enough about what k was. So if I use the with construct, what with does is, yes, I've only been typing for 30 odd years. I mean, why would I be good at it? So what with does is it introduces new patterns to the left-hand side. So by matching on k, it's either going to be parity k. It's either going to be even or odd. If it's even, then that means k has to have the form n plus n. There's no other form it could have. This type here says so. So A-R-I-T-Y. So that should be. I've called it J here. Let's call it N. We've now, by saying by using the with rule on parity and saying, okay, this one is even, then so this pattern here tells us that this k must have the form n plus n, and the answer is in that case going to be even of, well, effectively what we're doing is dividing the number in two here. So if you kind of work that out, you'll end up with, I'm going to call it j, because that n, this n refers to the n in even, and just for the sake of clarity, I'll call it j. Do we think that's going to work? No? Why is it not going to work? Oops. That's not what I meant to do. I'll give the whole definition, and we'll see what actually happens. If that's odd, then this is also going to be odd. And so you reckon that's not going to work? You're absolutely right. What it says is, no, sorry, I can't unify parity of successor j plus successor j with parity successor of j plus j. Now this is quite annoying, because you can all see that those two expressions are clearly equal, but the machine is not clever enough to do that. And it's basically as before, with the same as the problem we had before with n plus 0 equals 0, is that we can't fully normalize this because there's a successor on the right-hand side, which we're not pattern matching on. Now, the way to get around that is with using this operator. I pronounce that might equal. And what that gets the machine to do is type check both sides as normal. So they've got to type check independently, but it introduces a couple of new definitions into the context: parity lemma 1, parity lemma 2. So let's attempt to prove one. So let's just compute as before. So we'll get the normal form of that. I'll just go through this quickly. So this value here, this is the one we had, and this goal type, this is the one we need. So fortunately, there's a collection of lemmas in the library that allow you to do very specific rewriting on numbers. So the one in this case is it's called. It has the very. Your tab complete isn't working, David. Let's just type it out. It has the unfortunately wordy name plus sock right sock, and this sim just means apply the equality in reverse order. So that gets us to the position we want to be, and now that's, well, we've got something of the right type in the context. So just say trivial, and we're done. Question.
If you had two things with the right type in the context,
it picks the first one.
Okay. It may not be the one you're looking at.
No, you do have to be a little bit careful. You do have to at least think about your programs. Even though you've proved something, it doesn't necessarily mean you've proved the right thing. This is be careful there. Fortunately, the other proof is exactly the same. It just has a different name, so we won't bother. So now I can try something like, parity of 42. It's even, and it has lots of successes. If anyone fancies counting that that's really 21, then 42, then do. But I'm not going to. Okay. So everyone happy with that? Anything sort of weird about the reason for that, showing that really is why we need the with rule rather than just case. So using case on the result of that parity wouldn't have told us anything about why the numbers were even or odd. It wouldn't have told us anything about the structure of k. So we needed to have that just to get the structure of k. One final thing before we stop. Actually, before I go on, if you look in the code distribution, there's a subdirectory called binary, and that subdirectory binary has an implementation of a binary addition, where the binary numbers are parameterized over natural numbers, and the binary adder, the type of the binary adder says that this adder will produce something equivalent to the natural number addition. So just because that type check means that you don't have to run it to know that you've got a binary adder that works. So I was going to show you that in the lecture, but I decided there was clearly not going to be enough time to do that. but I've given you the code anyway. And the reason for showing parity is that actually that's an important point to how to construct the binary numbers in the first place. So taking a number as an input, you have to construct that binary number. So parity is a good way of doing it. Right, one last thing for today. So I want to show you about predicates on data structures. And to start with, the necessary thing is decidable equality. So Booleans aren't very useful if you're proving things about programs. Now, if you're programming in Haskell and you're checking two things for equality, you'll probably just use the eq type class, and that returns a Boolean that says whether your two things are equal. Knowing two things are equal is all very well, but if you want to prove stuff about it, you need to know why they're equal, because you're going to use that information later on in your proof. So this decidable equality type, or this decision type, you can read this as yes because and no because. So we have an A, we either have an A or we have a not A. This is what the decidable type does. So decidable equality says, given, so this is a type class just like you have in Haskell. There's nothing particularly special about type classes in Idris, except that they can have multiple parameters, and there's nothing to stop these arguments being values rather than types, so there's no restriction there. But other than that, it's really just for overloading. So this is, if I've got an x1 of type T and an x2 of type T, I can either show that they're equal or not. So this is the decidable equality type class. So if you've got an instance of decidable equality, you can provide two inputs, and you'll either get a proof that they're equal or a proof that they're not equal. Okay, so one possible use for this is in implementing a test for whether something is an element of a list. Now this data type is actually, I'll do this. I'll do this by hacking rather than going through the slide. So we have this data type called LM. It says that this thing, this first argument, is an element of this thing, of this list. So it's a predicate that proves that something is an element of a list. And this is a kind of prologue-style way of writing the program. We say, well, okay, X is an element of a list at the beginning, so it's here, if the list we're looking at is X cons X's. So X is an element of X cons X's. And assuming we can show that X is an element of X's, we can also show that X is an element of Y cons X's because it's somewhere in the tail. Now, one thing I want to show you before we go too much further on. So here I've had to give the type of X's explicitly, simply because A is not bound anywhere else, and it's not very good at making up names for things. If you have several, if you have this sort of thing, you know, this X's colon list A appearing a lot of times, it's often better just to list all of the implicit arguments. And you can do that with this sort of syntax. So this syntax just means every time you see X's in this block, make it an implicit argument with the type list A. So just to improve the readability of your code, and so that you don't have to type quite so much. So as an example of how that works, this in list, it's a proof that 2 is an element of the list 1 to 4. I mostly did this so I could show you the list range syntax. So list 2 is it's not the first element, so it's there, and it is the second element. So it's the first element of 2 to 4. So the proof is there here. This actually looks suspiciously like the natural number definition. You can pretty much use that to count. You know, there of here is 1. There of here is 3, sort of thing. So what are we going to do? We're going to try to write a function that tests whether something is in a list, and if it is in the list, it'll return a proof that it's in the list, because we might be able to do something with that proof later on, and it might be important to us later on. Right. So please feel free to shout out contributions to this solution. First thing we're going to do is, well, we're writing a function over lists, so the first thing to do is what do we do with the empty list? Well, that should be quite easy.
Nothing.
Yes. Does the machine believe us? I like to type check constantly. I don't know about other people when they're writing Haskell programs, say. I type check constantly because I like to find out early if I've done something wrong. Now, what about if we're testing whether x is in some list? Now, I can't just write x cons x's here because that's a non-linear pattern, and I can't help it. When my programs get beyond a certain threshold, I stop doing that, but we're not there yet. So what are we going to do here? Because we need to know whether x and y are equal, and if they're equal, if we just do a Boolean test, well, firstly, we can't do a Boolean test. Well, actually, we could because we've got nat. We can't just do a Boolean test because that doesn't tell us why they're equal, so we can't construct the proof of here. We can't know that x and x are the same thing. So what we can do is say, well, let's provide a proof of equality of the two. So let's decide equality between x and y. Now, if they're equal, we'll have some evidence that they're equal, which we can use in the definition. So we're now allowed to write, because of the definition of decidable equality definition of decidable equality, we're allowed to say is lm x cons x's, and dec eq gives us either yes or no. So yes, and some proof that we're not actually that bothered about, but we're just using this proof to show that these two x's are the same. So the only time you're allowed to have repeated variables on the left-hand side of a pattern match is if you have some evidence somewhere else that proves they're equal. So this thing here is what proves they're equal. So what are we going to do? Well, it's here, isn't it? So let's just return here.
Return?
Well, maybe it's a monad, isn't it? So we can return it. All right, all right. You'll regret that in a moment when we have to do something slightly more complicated. And in this case, it's no. So what are we going to do? Should we use case or should we use do notation?
Idiom bracket.
I'm glad you asked me that. Why don't we just say, well, we're working in the idiom of maybe. So let's just use idiom. I'll explain these in a moment. We need to check that whether x is an element of y's here, and if it is, we need to put it after a there. So that works. I guess I better explain what's going on here. I'll do it as I'll do it in do notation. So first thing we have to do is check whether x is in y's. Now, you're familiar with monads, aren't you? Most of you are Haskell programmers. So if this returns nothing, then that's okay. The whole thing is going to bob out and return nothing. If it's not nothing, well, we have p, which is a proof that p is an element of y's. And if p is an element of y's, well, you see here, if we've got an element, a proof that x is in the tail, then we can always stick another constructor on the front. So we can return there of p. Or okay, let's keep you happy. Let's return these just. Yes?
I'm just concerned there may be some people who don't know do notation.
I sort of have the impression that the Haskell programmers are happy. Is anyone not happy with do notation? Okay, let's go one step further back. Is lm of x, y will either return nothing or just. If it returns nothing, then the whole thing is going to be nothing. So notice, by the way, I've got a fat arrow here because I'm using the normal arrow for function application. And
You're missing off there.
oh, thank you. Thank you for averting the parse error, which was doubtless have given a ridiculous error message. It might return a proof. So it's either going to return nothing or just. If it returns the proof, then okay. So everything I've just written is equivalent to this. So what's happening with do notation is simply, I'm not going to explain this in detail, I'll just sort of gloss over it. If it returns just, then it binds to the P and you can carry on. And if it returns nothing, then the whole thing stops. Idiom brackets just go one step further and allow you to just do the application directly, just with less noise. So the definition I prefer for this one is that one, because it actually just looks like when you get used to sort of squinting, if you squint a bit, you see just the function application through the idiom brackets, and you've built that proof. Right. So I guess we should test that. Do we test functions around here? Yeah, let's test functions. What did I call the function? Is lm. Is 2 in the list 1 to 4? Yes, it is. It's just there of here. Is 5 in that list? No, it isn't. So I guess for those examples it works. There is actually a better way of doing this, which I'm not going to do in this lecture, but it might actually be better to return, instead of maybe LMXs, to return decidable element of X's. And that means if it's not there, we also have to prove it's not there. If I just put maybe there, I can legitimately define this function as, and no one's going to, type check is not going to have any problem with that. It's just not going to be quite what we wanted. Oh, and I guess we should once you finish something that's kind of proof-like, it's a good idea to tell the compiler that you expect that to be total. And reassuringly, it says yes, it is.
So why did you define the lm over natural numbers rather than?
Oh, just because I'd have had to do more parameterization and stuff. Okay. So one of the exercises, by the way, is to do it properly. Right. So that's all I wanted to talk about for today's lecture. That's kind of a very fast overview of some of the tools and techniques that you have available in Idris. So I guess it's time for a tea break, and then we'll come back and do some hacking.